All right, the last little piece. The Bohr Rutherford model that we all learned in grade 9 and grade 10 and know and love, it works really well. Like we can predict ion charges and some basic ionic bonding and some a little bit more about some more relatively uncomplicated chemistry. But from a physics perspective, it's completely flawed. The model is that the nucleus is small, dense, and positively charged, and that these wee little tiny electrons exist outside the nucleus somehow. Okay, here's the problem. The electrons can't be stationary, because if they're standing still, since opposites attract, they would get electrically attracted and fall into the nucleus, and the atom would collapse. So they can't be stationary, therefore they must be moving. Now, new problem, the electrons can't be moving because if they're moving, Maxwell's equations that I've mentioned before, they predict that moving charges, accelerating charges, give off electromagnetic waves, or basically they give off energy. And if they were moving, they would give off energy and would have the same outcome. They would fall into the nucleus and the atom would collapse. Therefore, they must be stationary. So we need a new model of the atom that has electrons that are moving, and at the same time, the electrons are stationary. Can you think of something, if you were alive at this time trying to build our new model of the atom, can you think of a model, a way to model the electron so that it's moving and stationary at the same time? Can you think of something we've learned in physics that is moving but stationary? We talked about it in grade 11. It came up in the waves and sound unit. Got anything? Standing waves are going to rescue our model of the atom. Standing waves are something that are, in a way, they're moving, but in a way, they're standing still. We've said that electrons are quantum particles and have a wave-particle duality. So instead of thinking of them as wee little tennis balls going around the nucleus, we need to think of them as having a wave nature and think of them more specifically as standing waves wrapped around the nucleus. Bohr's math that was verified with experiments, he said electrons can't just be anywhere and everywhere. They exist at very specific radii. And de Broglie's maths say electrons have rather specific wavelengths. So if we kind of add this idea of standing waves, what we're going to say is that electrons orbit the nucleus, they exist as standing waves, such that the circumference of their orbit must be a multiple of their de Broglie wavelength. So they can't just be anywhere. Whatever the de Broglie wavelength is, the first orbit, the first shell, I don't even know the right chemistry word to use, would be when there's one wavelength of distance wrapped around as the circumference of that electron's shell. The second shell would be 2 wavelengths. Third shell would be 3 wavelengths. This picture that I found online is a representation of the third shell. If we track it, this is a weird 3 wavelength long standing wave, but it's wrapped in a circle. So we've got like 1 wavelength gets us to there. That'd be 1 wavelength. 2 wavelength gets us to there. 3 wavelength gets us back to where we started. So if we picture the electron existing as a standing wave, then a multiple of its wavelength, wrap that around the nucleus, that's where those electrons are allowed. I couldn't find a picture of it, but if we had a picture of the next larger radius, it would have 4 of those wavelengths. The electrons aren't allowed to be anywhere in between the 3 and the 4. They could be in the 3 state, the picture there, or they could be in the 4 state, whatever that picture would look like, but they're not allowed to be anywhere in between. That matches the math that de Broglie gave. It allows for electrons. In chemistry, we talk about how we can't know their position for certain, and in quantum, we say it's based on probability. That kind of matches what we're going with this idea. If we model, sorry, I'm just going to read through this. If we model the electron as a standing wave, that fixes the issues we had before. They only exist at particular positions, which are energy levels you may have talked about in chemistry class. If we want to go from a low energy level to a higher energy level, we have to add energy. And if we go from a high energy level back down to a lower energy, they give off energy. So in chemistry, you learned about the emission spectra. That emission spectra would connect to falling from a high energy level to a low energy level. What's kind of cool is the math on the energy levels matches what people see in observations from experiment. So the fix is this creative way of thinking. Electrons exist taking advantage of their wave property as standing waves wrapped around the nucleus. I'm going to pause the video here. There's a couple cool things that we kind of ran out of time, but read through Heisenberg uncertainty principle. That'll come up in university. Basically, it just says you can't know everything about a quantum particle. If you know its momentum, then you can't know its position exactly. Quantum computers are a big thing. They take advantage of the superposition aspect of quantum particles, allowing them to do certain problems quicker than regular computers. Something else that's kind of cool, quantum cryptography. An outcome of a quantum thing is that observing a quantum system changes it. That means it's a little bit complicated, but if you had a message encrypted using quantum technology, if someone tried to eavesdrop on it, since they're observing it by eavesdropping and trying to steal your information, the act of eavesdropping changes the information. So as a sender of the information, you would know if someone's tried to crack your information. That's all I've got. If you've got any questions, it's pretty cool stuff. Shoot me an email, ask in our next Google Meet. When I learned this stuff, it was more science fiction-y, but there are now real-world applications. Depending where you head next, maybe quantum will be a bigger part of your career than you think. Thanks for your patience through all these videos, and email if anything's bugging you.